Okay, we're going to cover Unit 7 of Algebra 2. And this covers everything that you need to know about exponential functions and how we write exponential functions. There is no separate quizzes for these. This is the entire unit. So we're going to go over one question each for these, for each of the sections within the unit. Um, this is the first example problem, but before we even start that, let's go over how to write the exponential form of an equation. So an exponential equation is written in the form f of x or y equals a b to the x. A is our starting amount, and b is our growth factor. If so our starting amount's fairly straightforward. It usually tells us what the starting amount is. Sometimes it asks us to calculate that starting amount given our final amount or our ending value. So sometimes it asks us to find A, not normally though. A lot of these questions are going to be asking us to find either B, the growth factor, which is how much is it being multiplied by, or x, which is essentially the time, or the time sometimes is written to the power of t, like f of t equals ab to the power of t. So that's normally just our time. Um, so for this first equation, we have a growth factor of 0.87. And that's actually part of our answer here. It says every minute the concentration of this medicine grows by a growth factor of grows or shrinks by a growth factor of, and this says 0.87. So we have to figure out, is this growing or is this shrinking? So when we're looking at these, we have to decide, is B greater than 1 or less than 1? If B is greater than 1.0, then it's growth. So you can think of that as 100%. B is greater than 100% is growth. B is less than 1.0, it's decay, which is another word for that it shrinks. So this would be B is less than 100%. Okay, so this one is just it shrinks by a growth factor of 0.87. The rest of this is just saying that this medicine is ingested, its concentration changes over time, and we can see how it's changing over a period of time. So it starts with a concentration of 95. They give us the growth factor, and then T is how many minutes have gone by. So T is like the x-axis, and it will show us how many minutes has gone by. Just for this first one, we'll graph what the equation is on Desmos. Let me just type that really quick here in Desmos for us. Um, so this is 0.87 to the power of t. And here we go. Okay, so all I did was put this in Desmos and just write it in Desmos like this. So we're starting with somebody's taken this much medicine, and then this is saying what's happening over time. Well, usually our body clears out medicine over time, so that means that there's going to be less and less medicine in our body as time progresses. And so as you can see on the x-axis, this is going up by decimals. So it's going right now 7, 8, 9. And this is how many minutes have gone by. So if we change, we'll just change our x-axis really quick here. We'll change it so it's not moving up by so many minutes so quickly. Now we can see this a little bit better. So we're starting at 95. After 1 minute, there's 82.65 units of medicine. And it looks like it was talking about it's in milligrams per liter is what it's giving us, this 95. That's what the 95 value represents. And so as t gets larger and larger, the amount of medicine gets smaller and smaller. So you can see our y is going down as our x is going up. So now x is 3, y is 62, x is 4, y is about 54. Eventually, we'll get to no medicine in the body. Um, Medicines have half-lives, so it takes a very long time for any substance to leave the body completely. So that's why it's taking so much time to get to zero. So it's getting closer and closer and closer to zero. Eventually we hit zero medicine in the body, and we don't actually get a negative value because you can't have negative medicine in your body. And so this is just an example of an exponential curve that's showing us decay. And I'm just zooming in and out so you can see the different just the different ways that the graph can be represented based on the scale of the x or the y-axis. Okay, so all of these are going to be in this same or similar format. Now, sometimes t can be hours, sometimes t can be minutes. That just kind of depends on what the problem tells us. But for this one, it's talking about minutes. How many minutes have gone by? For every 1 minute, it decreases by a growth factor of 0.87. All right, let's look at another one now. This is on the next section from Unit 7. It says Bharat sent a chain letter to his friends, asking them to forward that letter to more friends. And then we have this exponential uh, formula here. Now, this is a little bit unique because it says t over 175. And we have to complete this sentence about the rate of change in the group of people who are going to receive this email from him. So let's take a look at the starting amount. There's 2,401. That's a little bit less important based on what they're asking us to find. It says the group of people who receive this email gains 1/7 of its size every how many days? So 8 over 7 is 1 and 1/7. That tells us that the 1 is the 100%. 1/7 means that it's more than 100%. So this is going to be growth. Um, every It says the group of people who receive the email gains 1/7 of its size every how many days. Now, if we look at the exponent here, this has t over 1.75. And if we're talking about, if we want to figure out how many days that it is, we want this to equal 1. So if it's 1.75 over 1.75, that would be to the power of 1, which would represent 1 day, or uh, 1 unit moving forward, or 1 unit of growth. So this one is 1.75 days. Every 1.75 days, it gets 1/7 larger. You can also think of it like this: 1 and 1/7 to the power of what makes it grow 1/7? Well, the 100 has to be there to make it growth. So we have 1/7 left over. And so to make it 1/7, 1/7 to the 1, that equals 1/7. And so to make this equal 1, t has to be 1.75. So now we're not saying t is every 1 minute. We're saying t is every 1.75 days. And this problem is just to show you that t doesn't always have to be in increments of 1. So we can sometimes write exponentials as fractions to represent that. All right, let's go to number 3. Number 3 is asking us to write the equation out based on this information. So Alyssa is an ecologist. She's studying the changes in populations of foxes over time, and she finds out that the population goes down by 1/18 every 2 months. The population of foxes can be modeled by this function P, and then T is the time represented in months. She first observed there were 185,000 foxes in the Arctic Circle. We want to figure out what this function is going to be. So again, when we're writing our exponential functions, it's ab to the x, y equals ab to the x. A is our starting amount, and this is just p of t, same basic idea as f of x. So A is our starting amount. We're going to write 185,000. When you type this in, make sure not to put the comma because it doesn't want you to put the comma in there. Just when you're putting this number in. And then we got to figure out what B is next. So it's losing 1/18 of its population. Don't write 1/18 for B. It's going to be 1 minus 1/18. And it's not to the power of t because we're not saying t is every 1 month. We're saying it's every 2 months, and that is t over 2. So once we simplify all of this, there we go. Once we simplify all this, this is 185,000. I'm going to not write the comma because we don't want to write that when we type it in, times 17 over 18 to the power of t over 2. And so that's how we would write this exponential formula given this information. All right, here's the next one. And each of these are different sections from Unit 7. So here's our next section. Now we're going to get into finding logs and natural logs. Your calculator has a button on it that says log. Sometimes they have a button that says ln. So there's log and there's natural log. And if you haven't learned about logs yet, that's okay. I'm gonna talk to you about just a couple of different ways to manipulate logarithms today, so that way you don't have to know everything about logarithms right now. But if you do know about logs already, that's great. That'll really help you with this problem. So for this problem, we want to figure out what t is. Um, It says there's an unknown chemical and it's losing mass over time. This is a common type of problem that we see in chemistry. So something is losing mass at a steady rate and it's getting smaller and smaller and smaller. And we can see that it's getting smaller because B is less than 1 here. Um, so we found they knew the initial mass was 120 grams, and then they found the decay factor, or we can still call it the growth factor, I suppose, but it's decaying because it's less than 1, 81 over 625. And this says complete the following sentence about the rate of change in the mass of the sample. Round your answer to 2 decimal places. And it says the mass of the sample decays by a factor of 3/5 every blank months. Now, when I first saw this, I thought this was tough to set up the equation for because we don't see 3/5 anywhere in this problem. But what we can do now is we're talking about a decay factor. That's our decay factor there. So if we write 81 over 625 to the power of t and set that equal to 3 over 5, I'm just going to erase that for a second. Now we can solve for t. And if you've used logarithms before, great. We're going to use logs to do this because if you don't know how to do logs and you just try guess and check, it would take a very long time. Might even not even be possible to solve without logs. So for logarithms, the basic rules of them are kind of just like regular algebra, where if you multiply by a number on the left side, you multiply by that same number on the right side, and then you get the value of two equal sides still. Because if you multiply by the same amount on both sides, then the equation is still true. You can sort of think of it that way. You can do what's called taking the natural log of both sides. So you can kind of think of it as like times the natural log on both sides. But it's called taking the natural log of both sides. You can also write log of both sides. Either way is okay. Usually when we learn logarithms, we start with log, but we're going to do natural log for this one. Okay, so now our calculator is actually going to give us answers for the natural log of these with number values. With natural logs and logarithms, we can use what's called the power rule. And this is just one rule of logarithms that we're going to use specifically for these exponential formula problems. The power rule, all it says is if there's a power, we move it in the front. And that's only when there is a log or a natural log. So now we have t times the natural log of 81 over 625. And that's equal to the natural log of 3/5. Now we just have a nice, easy algebra problem to work out. I'm going to divide by the natural log of 81 over 625 on both sides. That becomes 1. And now I'm just going to type this in the calculator, this natural log of 3/5. Now, when you do that, just make sure you close the parentheses at the end and press equals. And you're going to get a decimal that goes on, I believe, for infinity. So let's just go to maybe 4 decimal places out. That's fine. And then we're going to do the same thing for this one. Natural log 81 over 625. And this is negative 2.0433. Okay. And then we're just going to solve for what t is. I'm going to use the exact numbers that my calculator gave me. So I'm going back and pressing what this exact value was and then dividing by what the denominator's exact value is just to get a very, very exact number. And we just so happen to get a nice decimal of 0.25, a terminating decimal. So t is 1/4 or 0.25. So t is in, they give us t in months, so we don't have to do any other conversions here. And because it's asking us how many months goes by when the sample decays by a factor of 3/5. And this is 0.25 months. Okay, so I think that was kind of a tough question, especially if you haven't seen logarithms before. The next problem is, I think this is our last problem. The next problem tells us an equation, and we want to figure out, we have to do another conversion and figure out how many hours have gone by. So let's examine this in a little bit more detail here. We're going to use natural log or logs again. Um, so Gottfried wanted to see how contagious that yawning can be. He conducted a social experiment by yawning in front of a random large crowd, and then he watched how many people yawned as a result. And he has this relationship that's been elapsed in time. P minutes um, is 5 times 1.03 to the power of t. And we want to complete the sentence about the hourly rate of change in the number of people who yawn in his experiment. So it says every hour, the number of people who yawn. Now, I think they put minute here just so we would really know that it's minutes. It's just telling us twice. So t is in minutes. That's all that this is saying. And we want to change it to hours. So here's how we're going to do that. The the minute factor, if we said every 1 minute, that would be 1.03 to the 1. That would be 1 minute. And for an hour, you might have seen this already, and you might know this already. An hour, 60 minutes. So that would be our growth factor to represent 60 minutes. I'm going to call the hourly factor, I'm going to call that H. So we actually want to rewrite this like, we want to rewrite this so that we can write it in terms of H. Um, just double checking on something here. I believe we want to rewrite it like 1.03 to the power of H. Yeah, so we want to find what H is. So H is going to be, we're going to set H for the hourly growth factor equal to 1.03 to the power of 60. Okay. Now we're going to take the natural log of both sides. And actually, let me double check that I wrote this correctly. Okay, is that? Okay, so now we're going to take the natural log of both sides. So the natural log of H is equal to the natural log of 1.03 to the power of 60. I'm just going to write it like that because that's technically how we write those parentheses. Okay, now we're going to use the power rule. And we're going to bring the 60 down. So this is, I'm just double checking really quick to see if we can do this maybe without logs. And I think we can actually. I think we can solve this without logs. I think this one, yeah, this is already solvable without logs. I'm going to cross this out because we don't need that. Um, we already have an equation for what H is. 1 hour is 1.03 to the power of 60. But now if we want to write this like, if we want to write it like um, to the power of, if we want to say P hours of, instead of time for minutes, I'm going to write H for hours. This is 5 times, and we've got to figure out what number this is to the power of H. So we're still trying to figure out what B is for Y equals AB to the X. We just have to figure out what that value is. And so for that value, for our growth factor, um, it's going to be 1.03 to the 60. Maybe I should have used a different letter for, I'm just going to use K instead. It's K. It's fine. No, we'll stick with what H is. It's fine too. We'll stick with H. But this needs to be a different letter here. It's anyway. Let's not worry so much about that. The hours, though, is 1.03 to the power of 60. So it's 5.89. And this is going to be to the power of H. So technically this has to be a different letter is what I was getting at. This can't be, this cannot also be H if that's H. That's all I'm saying about that. Um, so to go back, we're going to go back to the beginning, go full circle again one more time with this. So for every minute, there's a growth factor of 1.03. For every 6 minutes, 60 minutes, there's a growth factor of 1.03 to the power of 60. If we figure out what that is, that's our new growth factor. And I said K, it's really our growth factor of B, but it's our other B value, so we can maybe write it B sub 2. That's fine also. And we can say that our initial growth factor, B sub 1, was 1.03. So our new growth factor is 60 minutes. 1.03 to the 60 is 5.89. And the decimal keeps going. I just rounded it to the nearest hundredth. So our initial value stays the same. We never change that 5. We're just changing our growth factor now. So it's 5.89. And now we can make a graph that shows us every hour of how much this is changing. This graph was going to tell us the same thing, but it's going to be every minute. And now this is every hour. And so this is going to be our final answer for this one. All right, so that's everything for Unit 7 of Algebra 2, exponential models and exponential equations.